Addition and multiplication are binary operations. This means they take in two inputs and spit out a new third output. They also have similar features. For example, they both have identity elements and inverse elements in their set. Identities are elements that don't change the original element. For example, 1 is the identity for multiplication because any number multiplied by 1 is itself. 0 is the identity for addition because any number added to 0 is itself. The 0 matrix is the identity for matrix addition since any matrix added to the 0 matrix is itself. The identity matrix is the identity for matrix multiplication since any matrix times the identity matrix is itself. The inverses are elements that take a number back to your identity. For example, 1/2 is the multiplicative inverse of 2, since 1/2 times 2 equals 1, the multiplicative identity. -4 is the additive inverse of 4, since -4 plus 4 equals 0, the additive identity. The additive inverse for matrix can be found by taking the negative of each element. Adding this back to our original matrix, we can see we get our 0 matrix. But what is the multiplicative inverse of a matrix? Well, it should be a matrix that we multiply to our original matrix that gets us back to our identity matrix. How do we find such a matrix? Well, that's the goal for the next couple of lectures. But first, we should go over general notation. Just like how our inverse function has this -1 up here, our inverse matrix also has a -1. So if f was my original function, then the inverse of f is f to the -1. If b was my original matrix, then b to the -1 is the inverse of my original matrix. In order for a matrix to be an inverse, you must be able to multiply it on the left-hand side of your original matrix and the right-hand side of your original matrix, and have them both equal to your identity matrix. Notice how in both scenarios we have a square matrix. In this class, we will only be looking at square matrices when finding inverses. So the identity matrix we're working with will always be the same size as our original matrix. Now we're going to look at how finding the inverse matrix is the same as doing Gauss-Jordan elimination. Here, I labeled the unknowns in red. So on the left-hand side, I have my variables vector column, and in the right-hand side, I have my inverse matrix. Remember how we solved for the variable column matrix? I took the coefficient matrix and combined it with the solutions matrix, and I created an augmented matrix. I'm going to do the same on the right-hand side for my inverse matrix. I'm going to take the coefficient matrix and put it on the left-hand side of my augmented matrix. But on the right-hand side, what I'm going to have is the identity matrix. Now it's just business as usual. I use Gauss-Jordan elimination to get an identity matrix on the left side of my augmented matrix, and whatever happens to the right-hand side of my augmented matrix will happen. So in the left side picture, the solutions to my variable column vector is the right-hand side of my augmented matrix. In the same way, for the problem on the right-hand side of the augmented matrix is the inverse matrix.